In today's lesson, we're going to talk about the evolution of the universe. I think it's better to call it the Big Stretch rather than the Big Bang. The stretch would imply that the space itself is stretching. So rather than talking about a Big Bang or some kind of explosion, what we mean is that the space is expanding. So the space is being stretched. All right, so let's talk about at the beginning where everything was created from a scientific point of view. Now, what we observe is that the galaxies are moving away from us. So let's just say that these galaxies are moving away from us. If you were to rewind back time, it would have gone in this direction. And because they're moving away from us, if you were to trace back, it would have started at a single point. So, what do we say? Rather than saying number one. So when t was roughly 0, space-time was created. So space-time created. And there was a singularity at that point. Infinitely dense. So I'm going to use this symbol as infinitely dense. So it's infinitely dense and hot. So it's infinitely dense and hot. The next stage is when t is equal to 10 to the power of minus 35 seconds, and that is when there was a rapid expansion, and we call this inflation. Everything was redshifted. At that point, there was no matter, and there was only electromagnetic radiation, and it was just mainly gamma photons. At this time, the temperature was around about 10 to the power of 28 Kelvin. Right, then it's 10 to the minus 6 seconds. What happens at that point? Then you have quarks and leptons. Quarks and leptons. They start to gain mass from the Higgs boson. They gain mass from the Higgs. Then when it's 10 to the minus 3 seconds, 10 to the minus 3 seconds, these quarks combine. So the quarks and the leptons, sorry, just the quarks, isn't it? The quarks combine. So the quarks combine into protons and neutrons. So those are protons and neutrons. And you have pair production as well. These gamma photons can create electron and positron pair. When it's roughly 1 second, the temperature is roughly 10 to the 9 Kelvin. And that is when matter has stopped, extra matter has stopped creating. So matter stopped being created, stopped being created. When it's 100 seconds, the protons and neutrons combine into deuterium, helium, probably some lithium and beryllium, and roughly 25% of the universe now, at this point in time, 25% of the universe is helium. There are no heavier elements. All right, so let's just quickly recap. At the beginning, time and space was created, space-time. If we were to rewind back time, what we see now, because what we see now is that the galaxies are moving away from us. So if we were to rewind time, you end up with a singularity. The singularity just means a point. Dense, infinitely dense and hot. Afterwards, there was rapid expansion. We call this inflation. At that point, there was no matter. There was only electromagnetic radiation, gamma, so gamma photons. And at that point, it was 10 to the power of 28 Kelvin. After that, you end up with quarks and leptons, and they gain mass through the Higgs mechanism, or the Higgs boson. After that, 10 to the minus 3 seconds, the quarks combine into protons and neutrons. You're not really expected to know these numbers, but you are expected to know all of these descriptions. The quarks combine into protons and neutrons. There's pair production, so the gamma photons can combine into electron-positron pair. Afterwards, after 1 second, the temperature is 10 to the 9 Kelvin and the matter has stopped being created. And then 100 seconds, protons and neutrons combine into deuterium, helium, lithium, beryllium, and about 25% of the universe is helium, and no heavier elements created. And then what happens after that? What happens after 100 seconds? Okay, so now when it's 380,000 years, you end up with atoms. Why? Because now it has gone cooler. So because it has gone cooler, it is condensing. The quarks and leptons, the protons, neutrons, they get closer together, they form atoms. The nuclei attracts the electrons, forming atoms. And the electromagnetic radiation, the gamma, becomes microwaves because it's red shifted. And then 30 million years now. So 30 million years. You end up with the first stars. And what happens within these stars? Nuclear fusion. And because of nuclear fusion, they start to make heavier elements. Heavier elements formed. 200 million. When it's 200 million, galaxies, the Milky Way, gravitational forces. So you've got the Milky Way formed. Other galaxies formed. And gravitational forces. Then what happens at 9 billion? Our solar system is formed. Now these types of large systems where you have planets and the star in the center, these were formed from supernovae. And then you have Earths and other planets, for example. And then life on Earth after 1 million. $13.7 billion. Modern humans. All right, so there you have it. After 100 seconds, we go straight into 380,000 years. The nuclear electrons, they combine into atoms because it has gotten cooler. The electromagnetic radiation, the gamma photons, have been redshifted into microwaves. 30 million years, the stars are formed, nuclear fusion begins, and it forms nuclear elements. 200 million years, the other galaxies are formed, the Milky Way is formed, and then gravitational forces between those galaxies. 9 billion years, the solar system is formed because of the supernovae, Earths and other planets are formed, and then after about 1 million, you end up with life on Earth. Modern humans is when 13.7 billion years after the Big Bang. Let's have a look at a 6-mark question. The Big Bang Theory is an explanation for the start of the universe. Explain how the cosmic microwave background radiation supports the Big Bang Theory for the start of the universe. Comment on the relevance of the data in figure 23.1 concerning the Big Bang Theory. This is 6 marks. So here is figure 23.1. So let's just go back to that data. So Andromeda Galaxy has a wavelength of hydrogen line from galaxy 485.6 nanometers. Wavelength of hydrogen line on Earth in nanometers is 486.1. Virgo cluster 489.8 nanometers. And it's the same 486.1 nanometers wavelength of hydrogen line on Earth. To answer this question, we need to compare the Virgo cluster and the Andromeda Galaxy. So I've made a table here where this is the galaxy's measurement and this is the Earth's measurement. So if you compare the Virgo cluster measured from that galaxy, compare that with the Earth, you can see the wavelength has gotten longer. So the wavelength has gotten longer. What does that mean? It means it has been red-shifted. It is moving away from us. This supports the Big Bang Theory. So that's Big Bang Theory. And now, because we see galaxies moving away from us, if you were to rewind back time, you would end up with everything in the universe at a single point. But now what we see is that galaxies are moving away from us because the light coming from those galaxies have gotten longer compared to the wavelength that you would measure from the Earth. So you would get a mark for saying the wavelength has gotten longer, it is redshifted. So the change in wavelength is caused by the motion of the galaxy. Yeah. So the change in wavelength is caused by that motion, caused by the motion. So it is redshifted longer because it's redshifted. That's one mark there. Well, that's 1 point. Moving away from us is another point there. It supports the Big Bang Theory. That's another point there. And there's a change in wavelength caused by the motion. Let's talk about the Andromeda Galaxy. So this is for the Virgo cluster. For the Andromeda Galaxy, you can see that the wavelength has gotten shorter. So wavelength has gotten shorter. And that would imply it is blue shifted. And it is moving towards us. The reason for this is of the gravitational attraction. So 1 mark for saying that the Andromeda Galaxy shows blue shift. So it is blue shifted. It is moving towards us. And this is due to the gravitational attraction. So those are those points. Now let's talk about what the Big Bang Theory predicts. So what does the Big Bang Theory predict? So the prediction of the Big Bang Theory is that the galaxies are moving away from us. Okay, so that's the prediction of the Big Bang. And we can talk about Hubble's law. So Hubble's law is h naught d is equal to v, or v equals h naught d, same. So the further away you are, so let's just say that's Earth, the further away you are, the faster it's going away from us. So here, if you are further away from Earth, it's moving faster. If you're here, it's moving much slower. That is Hubble's law. And then we can talk about the cosmic microwave background radiation. Now, at the Big Bang, at the point where the universe was created, there was only electromagnetic radiation. And these are gamma photons. So these gamma photons were created at the Big Bang. And because of the expansion of the universe, these gamma photons will be stretched. And they stretched, and what region do they become? They become microwave radiation. Okay, so you get a mark for saying that the gamma radiation at the Big Bang, they were formed. Because of the expansion of the universe, they get redshifted. We can also talk about the temperature of the universe. So that the universe is roughly 2.7 Kelvin. So it's less than 3, yes? So it's less than 3 Kelvin. Less than 3 Kelvin. And you can talk about that the radiation is uniform in everywhere. So the intensity of the radiation is uniform. All right, let's have a look at this question. This is a 4-mark question. The universe evolved from the Big Bang. Describe the evolution of the universe up to the formation of the first nuclei. If you're stuck, you can just go back to the beginning of the video. So these are 4 marks. How would you answer this question? Okay, so have you attempted the question? Okay, so the answer to this question is that, at the beginning of the Big Bang, you have a singularity. It is infinitely dense and hot. Okay, so that is the first point, because remember the question talks about up to the point where the nuclei has formed. Okay, so number 2, what can you say now? What was the second point? So the second point is when there was rapid expansion. For the second part, do you remember what else that we can write down? Gamma photons were created. Number 3. So before the nuclei were formed, what's inside those nuclei? You've got protons and neutrons. However, what's inside those protons and neutrons? Quarks. Then what you can say is that the quarks combine. And then what you can say is that these form nuclei. Okay, so there you have it. So they have to be in the correct sequence, any of those 4 points, but they have to be correct. When I say these, I mean these protons and neutrons.